Hello everybody, my name is Martin Whiteman. I work with ARM's Architecture and Technology Group. I'm a product manager responsible for the A and R profile architectures. What I want to spend the next 20 to 25 minutes doing is talking about how we are extending the architecture in 2021. So some background before we get into the new features. If you think about the architecture, it has a collection of different kinds of features. We can put these into 6 broad top-level categories, things like SIMD and security. And then we could look at the evolution of the feature set over time. Now, if you've attended events like this in the past, you'll have seen me or one of my colleagues doing talks very similar to this. We have an annual cadence for providing updates to the architecture and then talking to partners such as at Linaro Connect about what we're doing with the architecture. So looking at over time, if we went back to the V8 launch, so 2011, feature set might have looked like this. As we move through the IP generations, more jigsaw pieces arrive, bringing us up to 2020 and the V9 devices that got announced early this year. I'm not planning on talking about the features listed in these jigsaw pieces. They've all been previously announced. There's information about them that you can go read up or watch. But I'm showing it here as background because this is the foundation on which this year's extensions are going to build. So what are we adding in 2021? We're adding new instructions around memcopy. Memcopy widely used across lots of different kinds of software. So we're adding instructions to make memcopy more efficient on our platforms. NMI, non-maskable interrupts. Now, individual ARM CPUs, such as Cortex-R4, have supported NMIs in the past, but we've not had a standardized architectural feature. That's changing this year with an architectural NMI definition. And there's some other features which I'll talk about at the end, things like hinted conditional branches and new PMU events. Before I deep dive into those features, this talk is on the 2021 changes to the architecture. There are two I'm not going to talk about. They are RME and SME. The reason I'm not going to talk about these two is they were launched earlier in the year with their own launch events and announcements. So if you're interested in these two features, I'll give a very quick summary now, but please do see the ARM website for more information on them. So RME, or the Realm Management Extension, is part of ARM's confidential computer architecture. It's the CPU level extensions that builds on. That was announced at Linaro Connect today, back in June. So if you're interested in that, please do go and see the recordings from that event a few weeks ago. Scalable Matrix Extension, or SME. This builds on what we've done with SVE and SVE2 for vectors, adding new instructions to better support matrix operations. Again, not going to talk too much anymore about those today, but if you're interested, please see the links I've given, or you can contact me by email after the event. So the features we're going to be looking at for this year, memcopy and memset first. Just on these title slides, you'll notice the feat string on many of these slides. So if you've not come across this before, whenever we define a new feature in the architecture, we assign it a name, an identifier of this format. And I've included it because if you're looking for information in our manuals, then it's easier to control F for this kind of string. So memcopy, memset, again, widely used. I'm sure you're all familiar with it. I'm not going to talk about what they're for, but because they're so widely used, they're an important part of the performance and efficiency of a system. You want a good implementation of these library functions. Traditional risk answer was to say, well, use generic instructions to build up the sequence that you want. ARM is a risk-based architecture, so that is the way it is done today. The issue with this is there are many different microarchitectures of ARM, so different process designs, both from ARM's design teams and from our partners as well. The sequence that is optimal to do a memcopy can vary between the different microarchitectures. can also vary on things such as the size of the copy or the alignment of the copy. So what you see in many of today's implementations is that actually there are several versions of memcopy within the library, with some earlier code to try and work out which version to pick. We don't really want to have to do that. That's extra software maintenance, it's extra overhead in determining which version to pick, particularly if we're copying a small number of bytes that might represent a decent number of the execution time. So what we want to be able to do is have a single standard sequence for these different functions, which would be optimal across a range of ARM implementations. And that's what we're trying to do with this year's extension. So what we're doing is adding new instructions to support this, the copy and set instructions, copy for things like memcopy, set for things like memset. They both follow the same pattern, which is you can build one of these operations from a free instruction sequence. So if we take memcopy as an example, copy P is the preconditioning. It takes the arguments and gets and maybe does the first couple of bytes. Copy M is the main body of the operation. It do most of the copying of the data, and then copy E finalizes the operation. And so between these three instructions, you've implemented a copy or move operation. There's different arguments you pass on the instructions, so whether you want to do implementing a copy or a move, if you want to do it as unprivileged or privileged, temporal or non-temporal, and so on, but they will follow that basic pattern. Where I've put dest and source in brackets, those would be register arguments, so I've written them that way to hopefully make it a bit easier to read, but you would be passing them in registers. Now, obviously, for something like copy M, that instruction could be quite long if I'm copying a large amount of data. We can take interrupts in the middle of these sequences. So if I was partway through a memcopy, I could take an interrupt. When I return, the operation would resume from where it had finished. So they don't have to affect interrupt latency in this way. And yes, these are quite specialist instructions, but the idea here is that you would be able to write a standardized sequence that would be optimal across a range of different ARM implementations. So from a software point of view, this is far less software maintenance. I don't need to write or maintain as many new copies. I don't need to produce a new copy for a new implementation. For hardware engineers, this makes it much easier to detect sequences that represent things like copies and sets and do the required optimizations in the CPU as well. So that's memcopy and memset. Next, we're going to look at non-maskable interrupts, or NMIs. Before I talk about what we've added in the architecture, it's worth talking about why we're doing this. So we've not had an NMI for many years. Why do we feel like we need one now? So the feedback we've had from OS developers is that they want finer-grained control over interrupt masking. They want the ability to mask most interrupts while leaving some interrupts unmasked. Now, you can do that in today's architecture using the GIC and prioritization. The issue is that there's a lot of code already written that uses the existing CPU level masks, such as pstate I, which are binary. Either IRQs are masked or they are not. You can't mask some IRQs and not others. And because there's that existing code using the pstate masks, even though you could do this in the GIC, there's a desire to be able to do it in the CPU as well. So that's why we're adding a feature, and it explains some of what was going to come next. So here's my very high-level diagram of how interrupts work in an ARM-based system with a GIC and a CPU. So we have the system-level GIC, which we call the IRI in our manuals. This is responsible for prioritization and routing. The GIC CPU interface, which is the interface you work with to handle an interrupt, and the CPU or PE processing element. And what we're adding is changes both in the GIC and in the CPU. So within the GIC, we're adding a new attribute that interrupts can have, the imaginatively named NMI attribute. That's used by the GIC for prioritization. It's also presented to the CPU, and the CPU can internally use that for applying the pstate masks. So if we go into a bit more detail about this, What does that look like in the CPU? As I said, it's a new attribute for interrupts, which now I should say it defaults to being off. So unless you actively set something like, as an NMI, you'll get the behavior you see today. What the GIC uses the attribute for is as a formal priority. The GIC already has a prioritization scheme. NMIs are slotted into that scheme, as you can see on the diagram in the right. So a secure interrupt marked as an NMI becomes the highest priority secure interrupt in our priority scheme. A non-secure NMI becomes the highest non-secure interrupt in our priority scheme. We also changed slightly the way you acknowledge an interrupt in an interrupt handler, again, based on feedback from developers. They wanted to be sure that they could always guarantee to only get an NMI or guarantee not to get an NMI, depending on which interface they spoke to. So we now have 2 acknowledge registers. The original will never return an NMI ID. If the NMI is the highest priority interrupt, then it will return a magic value to say, go read the other register. And the new register will only return NMIs. And if the highest priority interrupt isn't an NMI, it will return a magic value as well. So that gives you confidence in your software. If I only want an NMI, I know I can get that. In the CPU, we've changed the way that the p-state masks are applied. So if you get an NMI signaled by the GIC, that information gets presented to the CPU. And as you might imagine, if NMIs are not affected by today's I and F bits, so if I get an NMI signaled by the GIC, even if the p-state I and F bits are set, that interrupt can still be signaled to software as an exception. Now, there are times, though, when we do need to mask all interrupts, including NMIs. One obvious example is interrupt entry. We need some period where we can save off our return state or loaded return state without it being corrupted. Other examples might be, there may be critical sections in your OS. You might be doing things with the MMU, for example, which means it's not safe to take any interrupt whatsoever. So we are introducing a new mask as well called allint, and as the name suggests, it affects all interrupts, including those with the NMI attribute. And this goes back to what I was saying earlier. It gives OS developers a level of control. You can now mask most interrupts using the traditional I and F bits. If you truly need to mask all interrupts, including NMIs, you can do that with this new control as well. We have a second mode available in NMIs, which you can select. What this does is to use the selected stack pointer as an implicit NMI mask. Remember what I said about an example of where you want to mask interrupts is on entry and exit, so that you don't corrupt your return state. Well, one of the things you see in the ARM architecture is we have different stack pointers. One stack pointer is always selected on exception entry. So we can use that as a pseudo NMI mask because it identifies a period when interrupts would typically need to be masked. But as I say, this is optional. You can choose to turn this mode on and off depending on how you want to handle interrupts in your OS. The next feature I'm going to talk about relates to the performance monitoring unit and BRB, the branch record buffer. So PMUs are used extensively for debugging and profiling. It's important that ARM platforms are a good platform to develop on. Hardware is ultimately only as good as the software that runs on it. We want it to be a good developer environment, which means being able to get good quality profiling information so that you can enhance your software. PMU is part of that. So this year we're adding new events around caches. In particular, what we're trying to do is make it easier to investigate the efficiency of prefetching. So how well is the process of prefetching data before you need it? And so to enable that, we've added events that tell you where data is coming from, which cache, which level of the cache it's coming from, so you can track that through the system. We're adding a threshold feature, so some events can increment by more than one per cycle. Think the number of FP operations in a multi-issue design, for example. The threshold feature allows you to say how many of those events have to occur in a cycle before I start incrementing the PMU. Another thing we're adding this year is related to BRB, the branch record buffer. Now, we talked about this last year, it was added in 2020. It's a feature to record history of the most recently executed branch instructions. That's useful for profiling, including things like auto FTO. When we first introduced it, it was restricted only to EL0, 1, and 2. We didn't support it in EL3. We've since had feedback that actually it's useful in EL3 as well. So we're now extending that to be supported in EL3 as part of the 2021 extensions. Other changes we are introducing this year, so there's support for hinted conditional branches. And it's important to say the hint isn't whether the branch is taken or not. The hint is that when you encounter this branch, it will behave very consistently. So an example of this is if you imagine a firmware image that you run on two devices, one device has a particular piece of hardware present, the other does the operation in software. So throughout that firmware image will be things like, if hardware present, then else do software routine. On a given device, the hardware is either there or not. So on that device, those branches will be very consistent in their behavior. But on the other device, a different device, they'll be very consistent the other way. The hint tells the hardware, once you can encounter one of these conditional branches, it will behave very consistently in the future. So if the first time you see it be taken, it will be consistently taken in the future. If the first time you see it not taken, then it will be consistently like that in the future. We've added traps around the random number generator. They take you to EL3. We've added a new algorithm as part of pointer authentication called Karma3. The reason for adding this is it gives benefits around things like latency, particularly for in-order designs. There's some new traps on EL0 use of ImpDef functionality in CPUs. And we've also added additional controls on EL0 cache maintenance operations, so you can change what kind of permissions these need. So those are the features we've introduced in 2021. I hope you found those interesting and are eager to learn more technical detail about them. So when will documentation be available for ARM? So the first thing that we'll make available is register and instruction set information in XML. Normally, we release these at pretty much the same time as Linaro Connect. This year, Linaro Connect is a couple of weeks earlier in September. So unfortunately, you will have to wait till the end of the month before we're ready to publish those, but they will be available very soon off developer. In terms of an an architecture reference manual, we plan for that to be available in the first couple of months of 2022. And then some of you might be familiar with our Learn the Architecture program. So as well as the, if you like, drier reference manuals that we've traditionally published, we're now also trying to publish introductory guides to introduce new features to our users. That you get off the ARM website, and we will be updating that to cover the 2021 features over the next few months. We're going to do it a guide at a time rather than a big bang, so you'll see updates throughout the rest of this year. And now, to do my finest Colombo impression, just one more thing before I go. Rules-based writing. So if you've been using some of our manuals, you may have noticed that we've been slowly moving to a new format or style called rules-based writing. Got an example on the right-hand side of the slide. And most recently, the RME, the Realm Management Extension, and the SVE2 supplements have adopted this style, so I'm sure at least some of you have already come across it. Now, that still leaves the main architecture reference manual, and the plan for that is we are going to move to rules-based writing, but we're not going to do it in one go. We're not going to replace the entire manual in one release in the new format. Instead, we're going to do it a chapter at a time or a couple of chapters at a time. And before we commit a new chapter into the published manual, we're going to release previews of that chapter on the website. I've given the link in the title of the slide, And that gives people a chance to get used to the new format, and we hope give us feedback on it. So I'd encourage anyone in the audience who uses our manuals a lot, please do take a look at the previews that we're making available, and tell us both what you like and what you don't like. It's, you are the users of the manual. We really do want to hear your feedback on the approach that we've taken. The one that you can currently get is the exception model, but more chapters will be arriving over the next few months for people to get feedback on. And with that, thank you very much for giving me your attention over the last 20-25 minutes. I hope you found that interesting. Please do contact me with questions. We should have a couple of minutes now, or you can get hold of me by email. It's on the slide here after the event. And again, thank you very much. Enjoy the rest of Linaro.